Yeah, welcome back to Laplace transformation part 7. Today we will see application of Laplace transformation for the solving of differential equation in IVP initial value problem as well as boundary value problem. We will also see how to solve simultaneous differential equation using Laplace transformation. So this lecture is basically based on the application of Laplace transformation. Till now we have studied in part 1 to 6. So let's start. Firstly, I am going to study the solution of differential equation. So for differential equation, I am going to here discuss some notations. I told you Laplace of ft I represented as fs, s greater than equal to alpha and alpha is greater than equal to 0. Now I'm going to solve the differential equation in variable x and y. So let's introduce some other notation. Then Laplace of xt I am supposing as capital X of s. Laplace of yt, if the differential equation in the term of y, then I am supposing ys. It means if we take the Laplace inverse of x of s, it will become xt, and if we take the Laplace inverse of y of s, it will become yt. Let's revise some important formula which will be useful today. So Laplace of f dash t, I told you this was sfs minus f at 0, small f at 0, and the Laplace of f double dash t was s square fs minus sf0 minus f dash 0, and Laplace of f triple derivative, third derivative, s cube fs minus s square f0 minus f dash 0 minus f double dash 0. So here our notation is going to be changed. If we are interested in Laplace of x dash t, it will become s into x of s minus x0. If we take y dash t, it will become s into ys minus y0. So whichever notation you are following, you can write the formula. I am going to write for second derivative in y again. It will be s square ys minus s at y0 minus y dash 0. Some other point are important. I told you the Laplace of yt is ys. Then the Laplace, if you multiply t, then it was multiplication property minus d by ds of Laplace, and it means ys. Or you can write minus y dash s because you are differentiating with respect to s. And I also told you if the Laplace of yt is ys, and if you integrate it 0 to t yt or y tau d tau. Some books write 0 to t y tau d tau, meaning is same. It is nothing else ys by s. We have to divide by s. I told you this property in lecture 2. Part 2 of the Laplace transformation. So this is the quick revision of the formula which will be useful today for the applications. So I'm going to study the solution of differential equation, initial value problem and boundary value problem. Initial value problem means both the condition are initial conditions for the second degree. We will get two conditions. Means all the conditions are given at only one point. And in the boundary value problem, we get the condition on the boundaries also. So let's start with the solution of homogeneous differential equation. And in lecture 1, I also told you for finding the solution of initial value problem in differential equation, firstly we find the general solution, then we find the particular solution for by the calculating the unknown C1 and C2, C3 and so on. But in the Laplace transformation, without finding the general solution, you can find the solution of given IVP or particular solution. So let's start with an example. So first example, I am taking very simple example, y double dash plus 4y equal to 0. I'm taking homogeneous differential equation. It is a second order differential equation. Y is 0, I am giving you 1. Y dash 0, I am giving you 6. So you can see that both the conditions are given at x equal to 0. It means the given problem is initial value problem. If these conditions are given at different points, then the problem becomes boundary value problem. So how to solve it? Here y is a function of x or t. If you are representing y dash by dy by dt, then it means it is given at t equal to 0. Suppose y is the function of t here, it means initial conditions are given at t equal to 0. It is y at 0, it is derivative of y at 0. So it is understood that y is the function of t. Let Laplace of yt equal to ys. Then I told you what will be the Laplace of y double dash t. I am not writing again and again inside t. It is understood that y is a function of t. It was s square ys minus s y at 0. This is capital Y, this is small y, minus y dash 0. You can see the formula I have discussed here. Now put the value which are given to you. This is s square ys minus y0 is given you 1, y dash 0 is given you 6. Now put now see the equation y dash plus 4y equal to 0. Take Laplace transform both sides. It will give you Laplace of y 4 double dash plus 4y equal to Laplace of 0. Linear property you can use. It will be Laplace of y double dash plus 4 Laplace of y equal to 0. Laplace of 0 is 0. It is s square ys minus s minus 6 plus Laplace of y I have already used. It is ys. I am not writing y is a function of t. It is understood now. It is equal to 0. Now put together the term of ys. It will be s square plus 1 ys and send remaining term to the right hand side. It will become s plus 6. Now you divide by s, coefficient by s in the right hand side. It will become s over s square plus 1. S square plus, I think I did mistake. It is 4 times. So it will be 4 times. It will be 4 times. Plus 6 over s square plus 4. Now we will take inverse Laplace transformation both the term side. Take inverse Laplace transform both sides. So Laplace inverse of ys is equal to Laplace inverse of s over s square plus 2 square. 6 I can take outside. Laplace inverse 1 over s square plus 2 square. Use the inverse formula. Laplace of y inverse will be yt. It is a Laplace inverse of cos 2t plus 6. It is the Laplace inverse of, I told you Laplace inverse of 1 over s square plus a square is 1 over a sine 80. It means h2 here sine 2t. So it will give you yt is equal to cos 2t plus 3 sine 2t. So this is the solution of the given IVP. Now how to check this answer is correct or not? So use initial condition, put t equal to 0. You will get cos 0 plus sine 0, 3 sine 0. Sine 0, 0, it means 1. If you derivate it and put t equal to 0, you will get 6. It means our answer is correct. So you can verify the answer here also. Now let's another example. I'm going to take small example 2 I am taking here. Example 2 is y double dash plus 2y dash minus 3y equal to 3 and y0 equal to 4, y dash 0 equal to minus 7, y dash 0 equal to minus 7. So this is a homework for you, similar problem. You can do this, but I think I have to discuss this. Let's start this problem. Let's solve. Solution. Solution. Take the Laplace both the side. Minus 3y equal to Laplace of 3. So separate using linear property. Plus 2 Laplace of y dash minus 3 Laplace of y. Laplace of 3 can be written 3 into Laplace of 1. 3 can be written as 3 into 1. So what is the y dash? I told you this is s square ys minus s into y0 minus y dash 0. This is the Laplace of y double dash plus 2 times Laplace of y dash is sys minus y0 minus 3 Laplace of y is ys and Laplace of 1 is 1 over s. Now put all the given initial conditions. This is initial value problem because both the conditions are given at t equal to 0. Minus 4s and this is minus 7, so it will become plus 7 plus 2 sys minus 4 minus 3ys is equal to 3 over s. Now kept ys together, it will be s square plus 2s minus 3ys. Send remaining term right hand side, it will give you 4s plus 1 plus 3 over s. Now divide by s square minus 2s plus s square plus 2s minus 3 both side. It will give you 4s plus 1 over. Factorize it. It factor are s minus 1, s plus 3. You can factor it plus 3 over s, s minus 1, s plus 3. Now I told you many ways you can use inverse method for that taking Laplace inverse both the side. You can use a residue method or partial fraction method. I am going to solve here by the partial fraction method. So before taking the Laplace inverse, I will advise you to break it in the partial fraction. So Laplace inverse of ys is, I am going to write the partial fraction directly. It are minus 1 over s, you can simplify it, plus 2 over s minus 1 plus 3 over s plus 3. You can break the partial fraction, you will get these fractions. So yt is equal to minus 1 Laplace of inverse of 1 over s is 1 plus 2 e to the power t. This is the Laplace inverse of twice e to the power t plus 3 e to the power minus 3t. You can verify the answer, put t equal to 0, you will get 4a. You can see this one, first condition is satisfying. This is the non-homogeneous differential equation. So I told you in the previous example, solution of homogeneous differential equation, and in this problem I told you the solution of non-homogeneous differential equation. So now I'm giving you some problem for practice. First problem is y triple dash plus 2y dash minus y dash minus 2y equal to 0, and given is y0 equal to y dash 0 equal to 0 and y double dash 0 equal to 6. This is the given initial condition. This is the initial value problem. You can see that. Second example I am giving you, x double dash t, here x is a function of t, minus 2x dash t. Here y is a function of t, but it is not given. Y means y is a function of t. Plus x of t is equal to e to the power t, and the given initial conditions are x0 equal to 2 and x dash 0 equal to minus 1. X dash 0 equal to minus 1. Now I'm going to solve a boundary value problem for you. Boundary value problem. Let's see a boundary value problem. This is an important example. Solve x double dash t plus 9 times x of t is equal to cos 2t using Laplace inverse, Laplace transformation. x0 is 1 and x pi by 2 is minus 1. So you can see that the value are given at two different points. It means the boundary interval of this problem is 0 to pi by 2. 0 to pi by 2. It means 0 and pi by 2 are boundary here. So it is a boundary value problem. So let's see the solution. So let Laplace of x of t is equal to x of s. Okay, then take, this is suppose equation number 1. Laplace transform both sides of equation 1. So you will get Laplace of x double dash t plus 9 times Laplace of x of t is equal to Laplace of cos 2t. Remember, you have to take Laplace right hand side also. Sometimes we forget to take the Laplace of right hand side. So it gives you wrong solution. So it will be x square x of s minus s into x0 minus x dash 0 plus 9 times x of s, and Laplace of cos 2t the s over s square plus 4. Now use the given condition. X0 is given, but x dash 0 is not given to you. Okay, no problem. X square x of s, x0 is 1. I am supposing x dash 0, let, here I am let x dash 0 is c. Now our aim will be to find the c with the help of this boundary. So minus c, I am taking as a c, plus 9x of s equal to s over s square plus 4. Now put that together, x of s coefficient, so x square s square plus 9x of s, and take minus x minus c right hand side, so it will become x plus c plus s over s square plus 4. Now you divide by x square plus 9, s square plus 9 both the side. You will get x of s equal to s over s square plus 9 plus c over x square plus 9 plus s over s square plus 9 s square plus 4. Now, if you take the Laplace inverse, this is very easy because this can be written as s over s square plus 9. 9 can be written as 3 square, so it is the Laplace of cos 3t. Laplace inverse of cos 3t. And this can be written as the Laplace inverse, its Laplace inverse, it will give the form of sin 3t. But this is very difficult. So for this, you can apply the convolution theorem, or I told you s over s square plus a square s square plus b square convolution theorem. But when a and b are distinct, here a and b are distinct, a is 3 and b is 2, we have a shortcut method. Let's see what is the shortcut method. This is very important shortcut method I am going to tell you. Kept s outside and break the partial fraction of 1 over s square plus 9 s square plus 4. And how to break these partial fraction? For breaking these partial fraction, I am going to solve here. Suppose you want to break the partial fraction of s square plus 9 s square plus 4. Suppose s square equal to some new variable v. Then it will look like v plus 9 v plus 4. We will break the partial fraction. This is a linear, and we can write a over v plus 9 plus b over v plus 4. If you see, you will get it is equal to v plus 9 v plus 4. You will get the value of a is minus 1 by 5 1 over v plus 9, and this value is plus 1 by 5 1 over v plus 4. It means now if you put the value of v here, you will get s square plus 9 s square plus 4 equal to, you take 1 over 5 outside, 1 over s square plus 4 minus 1 over s square plus 9. You can simplify it, you will get the same expression, s square plus 9 minus s square minus 4, so you will get the same answer. So what we did, we take s outside, because if s is outside, it will help you in the Laplace inverse of the cosine function. So what are the partial fraction? 1 over 5. Now you put s inside. So s over s square plus 9 minus s over s square plus 4 minus s square plus 9. Its partial fraction are 1 over 5, s is 1 over s square plus 4 minus s square plus 9. I kept it here. Now take the Laplace inverse. Take inverse Laplace transform. So it will give you xt equal to, this is the Laplace inverse of cos 3t plus c over 3 sin 3t, because this can be written as 3 square plus 1 by 5. This will be the cos 2t minus cos 3t. So what is your Laplace inverse now? Xt will look like now cos 3t. If you subtract minus 1 by 5 cos 3t, so ultimately it will be c by 3 sin 3t plus 1 by 5 cos 2t plus 4 by 5 cos 3t. Now how to find this value c? We will use the second boundary condition. Let's see how to use the second boundary condition here. So put xt equal to pi by 2 in both sides. You can find the value of c. So put the value equal to pi by 2 and simplify it. I am going to simplify here. So put equal to pi by 2. So x of pi by 2 equal to minus 1 equal to c by 3 sin 3 pi by 2 plus 1 by 5 cos pi, if you put pi by 2, plus 4 by 5 cos 3 pi by 2. So minus 1 equal to c by 3 sin 3 pi by 2 is minus 1, cos pi is minus 1, cos 3 pi by 2 is 0. So c you will get, the value of c you will get, that is 12 by 5. This is the value of c. Now you can put the value of c here. You will get the solution of the given boundary value problem. Put the value of c, you will get 4 by 5 sin 3t plus 1 by 5 cos 2t plus 4 by 5 cos 3t. So this is the way to solve this boundary value problem. Let's see one important example based on differential property. Solve t y double dash plus 2y dash plus ty equal to cos t, and given initial condition is y0 equal to 1. y0 equal to 1. If you see carefully, this is a very difficult second order differential equation. If you remember, I have studied 4 methods in Maths 2. First was variation of parameter. It is very difficult to find complementary function here. Then we have studied normal form, change of variable form, and one more method we have studied when one part of CF is known. But if you try by those methods, this question is very difficult. But by Laplace transformation, this is a very easy problem. So by Laplace, you can solve some very difficult differential equation in easy manner. So let's start. Let Laplace of y equal to ys. Then I told you, if you multiply by t in any function y t, it is nothing else minus d by ds of the Laplace. So it will be Laplace ys here. So I'm writing as minus y dash s. What is the Laplace of y double dash? I told you this is s square ys minus sy0 minus y dash 0. Now if you multiply by t, suppose this is your fs now. So it will be minus d by ds of fs. So you differentiate this Laplace s square ys minus sy0 minus y dash 0. So it will give you minus, it have two functions of s. First is outside derivative of ys is y dash s, plus ys is outside derivative of s square is 2s minus derivative of s is 1, so it will be y0, and derivative of this will be 0. So this is the Laplace of ty dash. Now if we take, this is equation 1, take Laplace transform of 1 both sides. What we will get? We will get minus s square y dash s plus 2s ys minus y0 plus 2. Laplace of y dash is sys minus y0 plus Laplace of ty dash is minus y dash s. You can see that, and Laplace of cos t is s over s square plus 1. So Laplace of ty is minus y dash. Laplace of 2 times y dash is sys minus y0. And ty, if you multiply by t, I will get this equation. Now if you simplify that, the minus 2s it will be cancelled by this term. And y0 is given to you 1. So if you simplify, you will get minus s square plus 1 y dash s equal to 1 plus s over s square plus 1. Now I am going to solve this equation. So you got now minus s square plus 1 y dash s equal to 1 plus 1 over s square plus s over s square plus 1. What we do? We divide by s square plus 1. So minus y dash s equal to 1 over s square plus 1 plus s over s square plus 1 whole square. Now take inverse Laplace transform both sides. So Laplace inverse of minus d by ds of ys. You can see that this is minus d by ds of ys. Laplace inverse of 1 over s square plus 1 plus Laplace inverse of s over s square plus 1 whole square. This is Laplace inverse of t y t. You can see that minus d by ds ys was minus t by t. You can see, I delete that. You can see previous 30-second video. So this is t by t, and this is the Laplace inverse of sin t. But problem is here. Now a and b are same, so we cannot use shortcut method I did in previous question. We have taken s outside and break the partial fraction. We cannot do here because both the fractions are same. So we had to use convolution theorem here. So Laplace inverse of s over s square plus 1 whole square. That can be written as Laplace inverse of 1 over s square plus 1 into s over s square plus 1. So call it as fs into gs. Now this is equal to f convolution of z of t. Ft was, or you can write ft convolution gt. Ft is Laplace inverse of fs, that is sin t, and Laplace inverse of gs is gt, that is cos t. So Laplace is given as, convolution is given as fu z of t minus u du. So here it is 0 to t. Fu will be sin u and cos gt will be cos t. So gt minus u will be cos of t minus u du. If you simplify it by multiplying 2 in numerator and denominator, you will get this is equal to t sin t by 2. Here, if you are not getting how you are getting ft is Laplace inverse of fs. So this is sin t, this is cos t. Now put here, it will give you t sin t by 2. So this is an important question. Now divide by t, you will get f by t. So yt sin t by t plus sin t by 2. So this is your yt. And if you use y0, sin 0 by 0, limiting case, it is 1 plus 0 is 1. So y0 is 1 given to you. It means our answer is correct. Our answer is correct. Okay, I am going to solve one more example based on the integration property. Firstly, I solved now homogeneous, then non-homogeneous, then boundary value problem, then multiplication by t. Now I am going to solve integration property. Differentiation I am already solving. So y dash plus 3y plus 2 times 0 to t y tau d tau is equal to t, and given condition is y0 equal to 0. So this is a very important differential equation which is very difficult to solve from the theory of differential equation, but by the Laplace transformation this is very easy. So I told you if the Laplace of y is ys, then Laplace of y dash is sys minus y0, and Laplace of 0 to t yt dt or y tau d tau, nothing change because integration property, first property, this is ys over s, divide by s when you integrate. Now take the Laplace of equation 1. take Laplace transform of equation 1. You will get Laplace of y dash. It means yes, ys minus y0 plus 3. Laplace of ys is ys plus 2, and the Laplace of 0 to t y tau upon d tau is ys over s, and equal to Laplace of t is 1 over s square. Laplace of t is equal to 1 over s square. Now y0 is 0 given to you, so it will simplified now. S, I am taking s as LCM, so it will be s square plus 3s plus 2 ys, and 1s is going to be cancelled out, so it will be 1 over s. Now ys will be 1 over s, factor s square plus 3s plus 2, it will be s plus 1 s plus 2. So you have three methods here. You can use a residue method, partial fraction method, or convolution theorem. So I am going to partial fraction method. If you break the partial fraction, a over s plus b over s plus 1 plus c over s plus 2. So the partial fractions are 1 by 2 into 1 over s minus 1 over s plus 1 plus 1 by 2, 1 over s plus 2. Take inverse Laplace transform both sides. So it will give you yt is equal to 1 by 2. This is the Laplace inverse of 1 minus e to the power minus t. This is the Laplace inverse of e to the power minus t plus 1 by 2 e to the power minus 2t. Now if you put t equal to 0, you can see that you will get y0 equal to 0. So this is the differential equation when we have integration term. Now let's see one more example which have Dirac delta function. You can also solve some problem which have unit step function, but I am going to solve for Dirac delta function because you will get the solution in the terms of unit step function. Plus 5y equal to delta t minus 2 Dirac delta function, and y0 equal to y dash 0 equal to 0 I am giving. Let Laplace of y is equal to ys, and we know that the Laplace of Dirac delta function t minus a is e to the power minus as. So use this property, take Laplace transformation of 1 both sides. What will we get? S square ys minus sy0 minus y dash 0 plus 2 sys minus y0 plus 5ys is equal to e to the power minus 2s, because a is 2 here. And you can see that y0 is given 0, y dash 0 is given to 0, so this term will be 0. Now s square plus 2s plus 5ys you will get only here equal to e to the power minus 2s. Now ys can be written as e to the power minus 2s. Completing the perfect square, it will give you s plus 1 whole square plus 2 square. Now take the inverse Laplace transformation. Take inverse Laplace transformation. So it is yt is equal to Laplace inverse of e to the power minus 2s over s plus 1 whole square plus 2 square. Now use the result. What is the result? Laplace inverse of e to the power minus as fs equal to ft minus a uat, second shifting theorem. So if you compare here this result, a is 2 and what is fs is? Fs is 1 over s plus 1 whole square plus 2 square. So ft will be attained by Laplace inverse of fs, that will give you ft. So what is the Laplace inverse? Firstly use the first shifting theorem, it will give you e to the power minus t. Then Laplace inverse of 1 over s square plus 2 square, that is equal to e to the power minus t by 2 sine 2t equal to ft. This is your ft. Firstly remove s plus 1 term using first shifting theorem, e to the power minus t will be outside. Now it will become 1 over s square plus 2 square, that is 1 over a sine 80. So ft is this. Now use this result here. So you will get ft minus a. You have f of t minus 2 u to t. So this is the Laplace inverse. Now put the value of ft. You will get the yt is equal to 1 by 2 e to the power minus t minus 2 sine of 2 t minus 2 u2 t. It can be breaked also. If t less than 2, this will become 0 because this value is 0. When t greater than equal to 2, this will become 1 by 2 e to the power minus t minus 2 sine 2t minus 4 because this value is 1. So this is the Laplace inverse of the given system, and this is the solution of the given differential equation. If you use the given condition y0, you will get t less than 0. T less than 2, it means y0 equal to 0. So this is another example based on the application of Laplace transformation. Now let's see the solution of simultaneous differential equation using Laplace transformation. So I'm going to solve here one problem also. Let's say differential equation dx by dt plus dx by dt plus 5x minus 2y equal to t, and the second differential equation is dy by dt plus 2x plus y equal to 0. Solution. And the given conditions are x 0 equal to 0 and y 0 equal to 0. Let Laplace of x equal to x of s and Laplace of yt is equal to y of s. Then we know that Laplace of this is nothing else x dash t actually. So x dash t is xs minus x0, but x0 is given to 0 here, so it will become s into xs. Laplace of y dash t will become sys minus y0, so it will become sys here because y0 is 0. Now take the Laplace of equation 1 and 2. Take Laplace transformation of 1 and 2 both sides. So what we will get here? We will get the Laplace of first equation as s(xs). First equation will imply x(xs) plus 5xs minus 2ys, and Laplace of t is 1 over s square. And second equation will implies that this is sys plus 2xs plus ys, and Laplace of 0 is 0. Now we can rewrite these two equations at s plus 5 into x of s minus 2ys equal to 1 over s square, call it as equation number 3, and second is 2xs plus s plus 1 ys equal to 0, call it as equation number 4. How we write it? We combined s plus 5, that's coefficient of xs, minus 2ys, and similarly for second equation. Now this is a look like a system of linear equation. We know that we have to solve a1x plus b1y equal to c1, a2x plus b2y plus c2 equal to c2. For finding x and y, we equate the coefficient. We multiply a2 here and multiply a1, then we subtract. So for finding x of s, firstly we will solve the equation for capital X, then we will put the value of capital XS, we will get the value of capital YS. So how to solve it? We will multiply by 2 here and we multiply by s plus 5 in equation 4 and then subtract. So what I am saying here, multiply, or you can multiply by s plus 1 here and multiply 2 here and you can add. So I can add, now I adding or subtraction, whichever you want you can do. Multiply by s plus 1 in 3 and 2 in 4 and add new equations. So you will get s plus 1 s plus 5 x of s minus 2s plus 1 ys equal to s plus 1 over s square. Now if you multiply by 2 here, you will get 4x of s plus 2 into s plus 1 ys equal to 0. Now if you add, these term will be considered. So you will get s plus 1, s plus 5 plus 4 x of s equal to s plus 1 over x square. Now what will be your x of s here? That will be s plus 1 over s square into s plus 1 s plus 5 plus 4. Now you can take Laplace inverse and you can solve for xt. You will get xt. Then similarly you can find yt by multiplying s plus 5 in equation 4 and multiplying 2 and then subtract. You will get ys. So okay, I am finishing here my lecture. This is the end of Laplace transformation from my side. Over now, in the next part, next lecture series, I will start Fourier transformation. Okay, thank you.